Hello guys. Last class we have discussed about the potential energy. Okay. Last class we started the potential energy. Okay. There we have discussed the potential energy means this is nothing but a stored energy. Okay. Stored energy. Okay. And we have discussed two examples. Okay. For spring system, one is compressed from on this compressed organs, the force exerted to compress the spring, the force is exerted to compress the spring, okay, or the work done on the spring to compress it, it gets stored, okay, it gets stored in the spring when it is in compressed form, okay. When you apply force or when you done work, when you do work during compression of the spring, what happens? Work done by us gets stored in the compressed spring, okay. So this stored energy is nothing but the potential energy. And second case we have discussed about the gravitational potential. Okay, so suppose this is surface of Earth and at a height h. Okay, so what is the stored energy or potential energy? Okay, the potential energy. What is the potential energy of a object which is at a height of h from the Earth? This is mgh. M is the mass of the object, g is the acceleration velocity, and h is the height from the surface of Earth. Okay, so this is the gravitational potential energy. Okay, now regarding the gravitational potential energy, we have to see some properties. Okay, so see how we represent the gravitational potential energy. Suppose this surface of Earth and there is an object at a height x. Okay, at a height x there is an object of mass m. So what is the potential energy? Suppose this is the object of mass m. So what is the potential energy of the object at this position? Potential energy is Vx is equal to x, means v is a function of distance. Okay, distance from the surface of Earth. So what is this? Mg x. Okay. Now, what is the force? Okay, what is the force required to? So, from when we see this, okay, so force required to lift the mass m at a height x from the surface of Earth. How much is the force? So, or the force required to lift the mass m at a height x from the surface of Earth is minus mg. Okay, we assign minus sign because the object is pulled by gravity with a force plus mg. This is a gravitational. Okay, and this much force or this much work or this much force is applied. Okay, this minus mg force is applied against this gravitational force to lift the object at a height h. Okay, so that's why as we are applying force against the gravitational pull, so we assign minus sign. Okay, we represent this force to lift the object. Okay, represent the force that is required to lift the object as minus mg. So this is the force required to lift the object against gravity at a height x. So if we see from one, what we get? Gx is equal to what? mgx. Okay, so if we differentiate 3x with respect to x, so what we get? dvx by dx is equal to mg. Okay, or you can write mg is what? Mg is the force required. Okay, mg is the force required to lift the object. So we represent this as mg as x. Say mg is equal to f. Okay, the force equal to lift the object at a height x. So dvx by dx is how much? Minus f. Okay, because I am writing minus because see this force is minus mg. Okay, this minus mg, say minus mg is equal to f. Okay, this is the force equal to lift the object at a height x. So what we get finally from this, what we get? Minus f is equal to dgx by dx, or you can write force that is required to lift the object at a height h, f is equal to minus dgx by dx. Okay, so this negative sign, okay, this negative sign indicates that we are doing work against gravity. Okay, the negative sign indicates that we are doing work against gravity. So this is what? This is a F is what? F is a force F due to gravity. Okay, gravitational pull or gravitational force. Okay, and F is how much? F is equal to minus dv by dx. Okay, so you can write force one. So you can write force in this form. Okay, okay. So we can write force F is equal to minus dv by dx form. Okay, this type of force. Okay, this type of force which can be write in this form. Okay, which can be write as the gradient, or it is also called gradient. Okay, gradient of potential. The force that can be write in terms of the negative gradient of the potential, this type of force are called conservative force. Okay, this type of force, okay, this type of force which can be write in terms of the negative gradient of potential, gradient of potential energy, this type of force are called conservative force. Okay, so what is conservative force? Definition: the force applied on a system which can be written in the form of negative, or which can be written as negative gradient of potential, which can be written as negative gradient of potential energy. Potential energy are called conservative force. Mathematically, how we represent this conservative force? F is equal to minus dv by, or minus dv by dx. Okay, so this is the condition for a force to be conservative. Okay, this is a condition for conservative force. That is, force applied in a system can be represented as a negative gradient of potential energy. Gradient means what? Gradient means ddx. Okay, differentiation with respect to distance. Okay, differentiation with respect to distance or length. This is called gradient. Okay, so F is equal to negative gradient of potential energy. So this is called conservative force. So gravitational force is what? It is a conservative force. Okay. Since gravitational force can be write down in terms of negative gradient of potential, so it is a conservative force. Okay. Now another thing is that I want to mention here. That work done by conservative force follows the law conservation of energy. See, earlier class what we told that I will discuss about the law of conservation of energy. Okay, that is like the law of conservation momentum. This is also same that during the whole process or during the whole time or during the whole process, during the whole time or during the whole process, what happens? The energy of the system. Okay, energy of the system remains constant. Energy means total energy. Okay, this means total energy. Total energy. That is kinetic energy plus potential energy. Okay, this is mechanical energy. Okay, this is the law of conservation of mechanical energy. Okay, law of mechanical energy. Okay, so mechanical energy means here this energy means total energy, and total energy in case of mechanical energy, what is the energy? Kinetic energy plus potential energy. Okay, so so work done by a conservative force follows the law of conservation of energy. Okay, so for a system which is doing work, okay, it will follow the law of conservation of mechanical energy only when the applied force is conservative. Okay, when the applied force is conservative, then only the system will follow the law of conservation of mechanical energy. So I will discuss this in this class after some time. The next thing I will discuss that, see, suppose this surface part and an object is at a height h. Okay, this is a surface of surface, and there is an object of mass m which is at a height h. Okay, so the forces that is applied on this mass is mg. Okay, downward. Okay, the force is mg due to gravitational force which is downward. Okay, so what is the potential energy of this body at this position? So potential energy will be how much? mgh. Okay, this is the thing we know. Okay, this body contains this much potential energy at this position at the height this. Suppose this is position A. Height is. Now suppose I drop the object. Okay, suppose I release the object from this position. So what happens? It will fall on the ground. Okay, with some or it will strike ground with some velocity. Okay, so when we release the object, its velocity, initial velocity is how much? Initial velocity is u. Suppose u is how much? 0. Okay, and suppose after some time it hit the ground. Okay, so this is the final velocity. Final velocity is how much? Suppose it is v. Okay, and here we know another thing is that the acceleration. Okay, what is the acceleration? It is z. Okay, it is the acceleration due to gravity. So here we can easily find the final velocity of the object v. So what will the final velocity? So final velocity v will be how much? So this v and this v are different. Okay, this is the potential. Suppose I am considering this final velocity is small v. Okay, small v is equal to how much? U plus a means g and p. Or sorry, I'm using this expression. T square equal to u square plus twice a s. Okay. And acceleration means what? Acceleration is acceleration velocity, and distance is as h. So this h. So u is what? U is 0. Which is 0. So what will be g squared? G squared is equal to twice g into h. Okay. Now if you multiply both sides by half into m, g squared is equal to half of m g h into 2. Okay, multiplying both sides by half of m. Okay, multiplying both sides by half of m. Okay, so what we get? Half of mg squared, here is the final velocity, is equal to mg h. Okay, so this is what we get. So from here what we can say that, see, this will also lead us to the concept of conservation of energy. See, initially it is at rest position at high h. So what is the potential energy at this position at point A? At point A, potential energy is P and kinetic energy is how much? So this is the, so what we get? Kinetic energy at point B. Suppose this is point G. Okay. At point B, kinetic energy is how much? Half of m v square, and we get half of m v square equal to mgh. Okay. So see, from up to now what we have obtained, initially the body has a potential energy mg is at a height is, it is at rest position at this at point A, and potential energy at point A is mgh. At point B, when it strikes the ground, the kinetic energy of the object when it strikes the ground, it is half of mv square. V is the final velocity of the object, and thirdly what we have, half of mv square, which is kinetic energy at final position at point B, is equal to mgh. Mgh means potential energy at point A. So from here you can go to the conservation, or you can see how energy is conserved in this system. Okay, so now at point A, so at point A, what is the total energy? At point A, total energy will be how much? Total mechanical energy how much? It is the sum of kinetic energy plus potential energy. So at point A, what is the kinetic energy? Velocity is 0, so kinetic energy will be 0. And what is the potential energy? mgh. Okay, so energy at point A, total energy at point A is mgh. Okay, now at point B, total energy is how much? See, at point B, so see, here height of the object from the ground is what? 0. Okay, at point B, what is the height of the object from the ground? It is 0. So potential energy at point B will be how much? mg. Potential energy at point B will be how much? mg into height is 0. So potential energy will be 0. So potential energy is, in this case, is 0, plus kinetic energy will be how much? Half of mv square. Half of mv square. Okay, so at point B, total energy EV is equal to half of mv square. Okay, so this is the total energy of this object at point A, and this is the total energy of the object at point B. See, from 1, what we have, a half of V square is equal to mgh. Okay, so we can say that since half of mg square is equal to mgh, so we can say that EA is equal to ED. Okay, that is total energy at point A is equal to total energy at point B. Okay, this is nothing but the conservation of energy. Okay, that is total conservation of energy. What is the law of conservation of energy? That for a system, if it is for a system, okay, if the applied force or force acting on a system is conservative force, then the total energy of the total energy of the system, okay, total energy of the system, okay, during during the whole process is will remain constant. Okay, the total energy of the system during the whole process or total energy of the system will remain constant. Okay, in case of applied force is conservative force. Okay, so see, initially it is a total energy at point A, total energy at point B. So see, at this initial and final point, okay, initial and final position, the total energy is constant. Total energy of the body of mass m is constant. Okay, so from here we can say that from here this is proof that in case of acceleration due to gravity or gravitational pull, gravitational force, the law of conservation of energy is valid in case of gravitational force. So this is the thing. So up to now what we obtained, that for a force to be conservative, what is the condition? This should be del v by del x. Okay, or you can write this f of dx is equal to minus del v. Okay, or I can, if you integrate this from initial to final position, f of dx, okay, is equal to how much? Vi to vf del v. Okay, or you can write this dv by dx actually. Also del v by del x, so it will get confused if I use del v, so it is better if I use dv. So Vi means what? Potential energy of the system at xi position, and Vf means potential energy of the system at final position. So from here we can write integration of f of dx, okay, from xi to xf is equal to Vf minus df minus Vi. Okay. So or there is a minus sign, or we can write, if we eliminate the minus sign, this is Vi minus V. Okay, so this is the work done by conservative force. Okay, so this is the work done by conservative force. Okay, so this is how we represent conservative force. Okay, this is a condition for conservative force. This is the condition for conservative force, and from here we can obtain this. Okay, so in case of conservative force, the difference in potential energy gives the work done by that force. Okay, in case of conservative force, the difference in potential energy, okay, potential energy Vf gives the work done by that force. Okay, giving the displacement from xi to xf position. So what potential energy is applied. Okay, So when potential energy is arises, so when potential energy arises, or so now where you can use the concept of potential energy. Okay, so potential energy arises, where it arises, only that type of forces where the work done by the force is or force gets stored in the system. Okay, so potential energy arises only that type of forces. Okay, potential energy arises due to work done for only that type of forces where the work done by the force gets stored in the system. Okay, system as energy. So potential energy arises only that type of forces. Okay, potential energy arises only that type of forces where the work done by the force is gets stored, okay, in the system as energy. Okay, see in the gravitational potential, when you leave the object, what happens? Work done by us is what? We work done against the gravity, mg, gravitational force. In distance covered is what? Mg. Suppose the height is mg. Okay. So what is the potential at this position? Mg h. Okay. So work done by us is gets stored in this object when you leave the body against gravitational force. Okay. So this type of forces, this type of cases, or this type of system, the potential energy arises. Similarly, during compression of spring, what happens when you compress the spring? The force applied by the finger, to the spring is gets stored. Okay, when it is in compressed form, what happens? The force applied by us to the spring is gets stored in the spring. Okay, so this total energy equals potential energy. Okay, so in this type of cases, this type of system, potential energy arises. Okay, the concept of potential energy comes in only that in this type of cases. Now, we can write. So up to now, what is it? That is equal to minus dv by dx. Okay, so this is the condition for force to be conserved. What is the potential energy in the system? Okay, and as the applied force. What is the dimension of potential energy? Okay, dimension of potential energy V energy. So it is same as the dimension of energy. Okay, this is ml square divided by minus. Okay, it is same the unit of energy. Now conservation of mechanical energy. What is a mathematical statement? Or so now this is the conservation of mechanical energy. There is a small derivation, okay, for this conservation of mechanical energy. Okay, so up to now, what we get from, I'm going to derive the conservation of mechanical energy. Okay, so from Newton's work energy theorem. What we get from Newton's work energy theorem? What we get? Change in kinetic energy delta K is how much? Applied force into displacement. Okay, change in displacement, change in distance. Okay, so what we have got earlier, that from Newton's work energy theorem, delta K, this change in kinetic energy is equal to the applied force into change in displacement. Okay, actually del x. Okay, now what we get in case of conservative forces, if F is conservative, okay, in the conservative forces, what we get? Change in so what we get? What is condition for conservative force? Minus dv by dx. Okay, so dv by dx means what? dv means small change in v. Okay, dv means change in v and dx means change in distance. Okay, so dv means what it is? So we can write this as change in potential energy by change in displacement. Like we have derived, okay, like we have derived, what we have derived? Vi minus Vr, okay, is how much? Integration of xi xs f of dx. This is nothing but a long term. Okay, so change in potential energy is equal to the work done by the force F, done by the conservative force. So you can write this, or you can also write this as minus del v by delta x. Okay, so we can write this like this. Okay, so how you can write del v is what? Del v is equal to minus f of delta x. Okay, this is number 2. Okay, so from Newton's work energy theorem, what is the delta K is equal to f of del x. Okay, so now from conservative, now if the force is conservative, okay, so two things we have got from Newton's work energy theorem. Delta K, this change in kinetic energy, is equal to f of f into del x. This is both done. And if the force is conservative, what is the condition? F is equal to minus del v by del x. Okay, the force is conservative. Okay, this is the condition. This is force is conservative. So f is how much? Minus del v by del x. Okay, so from here we can write, we can find del v is equal to minus f of dx. So this is the potential energy, okay, stored in the system. Okay, system where F is the conservative force. Conservative force is applied on the system. Okay, so now what do we do? 1 plus 2. Yes, if we do 1 plus 2, then what we get? Delta K plus delta V is equal to how much? This will get cancelled. F of del x minus f of del x, so it is 0. Okay, or we can write delta K plus V is equal to 0, or K plus V means what? Delta total energy. Okay, 0. Okay, so delta total energy, that is change in total energy. Okay, change in total energy with respect to distance. Okay, change in total energy with respect to distance is 0. Okay, this is what we get. So from here what we can conclude? from here we can conclude that, see, for any system, okay, for any system, suppose y is equal to 5, okay, y is equal to 5, or it is any constant of 5, okay, y is equal to 5. If we differentiate this, okay, dy by dx, okay, then what we get? 0. So that is, what does means? When y is constant, okay, y does not vary, when y do not vary, what happens? The change in y with respect to x is what? 0. When y is constant, then dy by dx, that is change in y with respect to x is 0. So when the derivative of any function, when derivative of any function is 0, derivative means change in this function or change in the value of this variable with respect to distance, okay. Dy by dx means change in the value of the variable y with respect to x, okay. So when derivative is 0, derivative of a function is 0, what does it mean? It is a constant, okay. The function is constant, okay. Function is some constant, and derivative is 0, what does it mean? Y is equal to constant, okay. Does not vary with respect to x. So see, delta means the change in total energy. Delta T plus B means the change in total energy, which is 0. That is, with respect to distance from her, you can say that with respect to position, the total energy does not change. Okay. So during the whole displacement, so during the whole displacement, total energy of the system is constant, okay. So you can write it mathematically as delta T plus V is equal to 0. That is, change in total energy is 0, or the total energy is constant in this system. So this is nothing but the law of conservation of mechanical energy. Law conservation of mechanical energy. Okay. So this is a law of conservation of mechanical energy. Okay. So how to look at? From Newton's second law, we get change in kinetic energy is equal to F into dx. Then from conservative force, condition of conservative force, we get F is equal to minus, or V is equal to minus F of del x, del v. Already increase to what we get? Total energy of a system remains constant, okay, during its whole displacement. So this is the law of conservation of energy. So for a system so the system will follow the law of conservation of energy. Law of conservation of energy with applied forces. Applied force is conservative. Okay. Only that If the applied force is conservative, only then the system will follow the law of conservation of energy. Okay. So up to now, what we can conclude? So to now, what we get? The force is conservative if F is equal to minus dg by dx. Okay. Now second thing, we have concluded that work done by the system is kf minus ki, or work done by conservative force is what? Changing kinetic energy, that is final kinetic energy minus initial kinetic energy, and changing potential energy, that is here in this case minus delta. Okay, or you can write minus Vf minus Vi. Okay, so work done by conservative force is how much? Kf minus Ki, that is changing kinetic energy, or minus Vf minus Vi, that is changing potential energy, or we can write then using the minus sign Vi minus Vi. Okay, so work done by conservative force, we can write Kf minus Ki, the final kinetic energy, initial kinetic energy, or we can write Vi minus Vi, initial potential energy and final potential energy. This means potential energy at the position xi, and this means potential energy at the position xi. This means potential energy at the position xf, and this means potential energy at the position xi. This is the thing that we have to keep in mind. So now we'll and third question is that work done by conservative force. Okay, so third, there is another property for conservative force, which is work done by a conservative force in a closed path. In a closed path is how much? It is 0. Okay. So these are the three properties for conservative force. So for the condition of conservative force, absolute minus dg by dx, and work done by conservative force, you can write kf minus ki or Vi minus Vi. And third is work done by conservative force in a closed path is 0. Okay, so if we see this, okay, what does it mean? How we represent the work done? Work done is what? F into delta x. Okay, or F is equal to delta x means xf minus xi, changing position. If xf is equal to xi, that is initial position and final position is equal, that is work done in a closed path. Okay, suppose I'm starting for this xi position, and this is, and doing some applying some force at some object at initial position, and during the whole displacement, the path traced by the object is cyclic or closed path. Okay, the path traced by the object is closed. Okay, it is initial position and final position are same. Then what happens? If we put xi equal to fx here, it will be 0. So work done is 0. So in case of a conservative force, the work done by a conservative force in a closed path is 0. Okay. So these are the three properties of conservative force. So up to now we have discussed the conservative force and the law of conservation of energy. Okay. regarding this, we have to take the example of spring, then the example of the gravitational pull or gravitational force. Okay, now so what is the law of conservation of energy? It states that the total mechanical energy of a system is conserved if the forces which are doing work are conservative. Okay, so what is the statement of law of conservation energy? It is the statement is that the total mechanical energy, that is total energy means the kinetic energy plus potential energy. The total mechanical energy of a system is conserved or constant if the forces, okay, which are doing work, okay, are, this is the earth surface and lifting an object at a height capital H, okay, object of mass m and lifting at a height of capital H, okay. So at point A, we have derived the total energy is what? At point A, what is the total energy? mg into h, okay. And also this is, suppose this is the point B, okay, point B. If we drop the object or if we release the object from this point A, then what is the total energy when it strikes the ground? Total energy will be what? EV will be how much? It is half of mv square. V is the velocity of the object at point B. Okay, and earlier what we derived that half of mv square, V is the final energy, V is the velocity of the object at this point. Suppose I am writing this V1. Okay, half of mv1 square is equal to mg into h. These are things we have derived earlier. Okay, now I go for another point. Suppose at this point, this is the point C. Okay, so my motive is to find the total energy at point C. So what is the total energy? Total energy at point C. Okay, so earlier we have derived that total energy at point A is equal to the total energy at point B. Okay, from this expression, the m half m1 square is equal to mgh. Then from this expression we can say that total energy at highest point is equal to total energy at the lowest point. Okay, now I am taking another point between these 2 points. Okay, between this point A and B, I am taking another point C. I have to derive the total energy at point C. So how we derive this? So how we evaluate this? So say suppose I am taking this height. So what is the height? Okay, suppose this height is how much? This height is small h. Okay, this point C. Okay, point C is, what is the height of point C from the ground? Height of point C from ground. How is the height? This h. So what is the potential energy at point C? Vc is how much? mg into small h. Okay, so at point C, potential energy at point C is how much? mg into small h. Okay, now you calculate the kinetic energy at C. Okay, C. when you leave the object from point A, okay, so what happens? It will acquire some velocity, okay, when it goes down. Acceleration of the this free falling is how much? This g. This is it's called the acceleration due to gravity. Okay. So from here we can find, see, during this part, okay, during this part, we know the acceleration that at which the body is falling. We know the initial velocity, that is which is 0, because the body is initially at rest, so we can find the final velocity. And also we know what? We know the distance between the point A and point C. Okay, so distance between A and C. Okay, it is how much? Capital H minus h, small h. Okay, distance between h is h minus small h. Capital H minus small h. So from here, suppose velocity at point C is how much? Suppose say velocity at point C is how much? Small v into c. Okay, velocity at point C is c. And we know the initial velocity, that velocity is point A is 0. Initial velocity, that is velocity is point A, that is u is equal to 0. So we can write, you know, that from the expression we can write that v square equal to u, from the expression v square equal to u square plus twice as, we can write v square equal to u means 0, 0 plus 2, a means gravitational pull, gravitational acceleration due to gravity, twice g into h means what? What is the height? The distance separation between the point h minus capital minus small h. Okay. So from here we get the velocity at point C. See, this is potential, capital V. Okay, and this is small v, small capital V. So this is potential energy at point C, and this is small v c. This is velocity at point C. So velocity at point C is 2 g h minus small h. Okay. Now what to get? So sorry. Okay. So we get the velocity. So what is the kinetic energy? So our motive is to find the velocity at point C, velocity of this mass at point C. From this velocity, what we do? We will derive the kinetic energy. Okay, kinetic energy. How much kinetic energy at point C? Okay, kinetic energy at point C is how much? Half of m into small g c square, and it will be how much? Half will get cancelled, m will add. Okay, mg h minus small h. So we know the kind total. So now up to now what we know? Kinetic energy at point C, this much, and potential energy at point C is how much? Capital VC is equal to how much? mg small h. Okay. So what will be the total energy? So we know the kinetic energy at point C, and we know the potential energy at point C. So what is the total mechanical energy at point C? So total energy at point C. So what it will be? Kinetic energy plus potential energy at point C. So it will be how much? mg h minus h plus mg into h. Okay, and from here, if we solve this, what we get? This will term get cancelled, mg into h. So see, I have taken an arbitrary point C between the two, between the initial and final positions. So when the highest and the lowest point, I have taken any arbitrary point C, and at point any arbitrary point C, what is the total energy at any arbitrary point between A and B? It is also mg h. Okay, so total energy at point C EC is equal to mgh. Okay. So earlier what we get, total energy at point is E is equal to mg into capital H. Okay, and total energy at point C is also mg into capital H. And at point B, total energy how much? Half of m v1 square. V1 is the velocity of this body at point B. Okay, and another thing we obtain earlier, we obtain another thing that half of m v1 square is equal to m v h. Okay, we have derived this in the earlier test. Okay, that is total, that is kinetic energy at the lowest position, okay, is equal to the potential energy at the highest position. Okay, and this place. So from here, EB is equal to EA. Okay, and EA is equal to EC is equal to EC. So from here, what we get, total energy of this body of mass m remains same during its whole path. Okay, so this is how we have verified. So we have verified the law of conservation of energy in gravitational force. Field. So in case of gravitational field, the law of conservation energy is verified. Okay, like this. Okay, so we verify the law of conservation energy in case of gravitational field or gravitational force. So next thing we'll discuss about the, see, earlier we had discussed earlier we have in the chapter 5. Okay, in circular motion. Okay, when we study about circular motion, what we have calculated, what we have discussed about a problem that a body of mass m is rotating a vertical circular path, and we have calculated its velocity, minimum velocity at its highest point. Okay, minimum velocity at highest point during its circular path. Okay, here after studying the conservation of law of conservation energy, we can obtain or we can calculate the velocity at the lowest point. Okay, so this point A is point B. Okay, earlier we have calculated what is the minimum velocity at point B such that the body of mass m can complete this circular path. Okay, now I've said in that class that I will calculate the velocity at this lowest point at point A when we discuss about the law of conservation of energy. So in the next class, we'll calculate velocity at point A. Okay, at this lowest point of the circular path, vertical circular path. Okay, so up to now I've discussed. Okay, thank you.